Let's discuss a fundamental concept of engineering mechanics of solids in this video, that is stress. You must have heard and studied of stress in your previous classes. However, we discuss stress in a bit more detail in this video. Investigation of internal resistance of bodies that are acted upon by external forces are a major area of study in engineering mechanics of solids. So we are investigating internal resistance, that is of bodies that are acted upon by external forces. And this will lead to the definition of stress. Once you understand the internal resistance, then you can evaluate, or you can find out what a stress is. So let's first see what internal resistance is. For that, let's consider a body which is under action of a couple of forces, say F1, F2, F3 and F4, and we also assume that the body is in static equilibrium. So the body shown here is acted upon by four forces, F1, F2, F3 and F4, and still is in static equilibrium. Now, because the body is in static equilibrium, the forces acting upon the body should satisfy the conditions of equilibrium. We discussed the conditions of equilibrium in a video here, and we derived the equations of conditions of equilibrium in the video here. And just to remember you, the conditions of equilibrium are summation of forces in x direction is 0, summation of forces in y direction is 0, and summation of moments in z direction is 0. So if the body is in equilibrium, then these three should be satisfied. These are called conditions of static equilibrium. Now, for analyzing the effect of the applied forces, we create we divide the body into two sections, which is divided by an arbitrary plane, and we can select the arbitrary plane anywhere. This method is also called the method of sections. Again, we discussed method of sections in this video here, where we analyzed perfect frames. We analyzed perfect frames using two methods, method of sections and method of joints. Method of sections use a section or an arbitrary plane to divide the frame into two and then analyze it. It is sort of same concept that we apply here. We divide the body into two parts using an arbitrary plane. So you can see here the body is divided into two planes. Here it is divided into two planes using an arbitrary plane, say ABCD. And because we know the body is in static equilibrium, so if you divide the body into two components or two parts, each part should be separately in static equilibrium as well. So that is the concept of equilibrium. If a body is in equilibrium, every part of the body should separately be in equilibrium. So that is an assumption, that is a condition we apply here. So we divided the body into two parts using an arbitrary plane. Now we can consider a single part of it. Say you have forces F1 and F2 here. Now the condition is, because the body is as a whole in equilibrium, this part of the body should also be in equilibrium. So if these forces, we know there are two forces applied on the body, so if this need to be in equilibrium, there should be some forces on the cut plane here. And those forces that are within the body are called internal resistance. Let's say delta P. 1 delta P 2 delta P 3. And these forces are developed in such a way that the body still remains in static equilibrium. In other words, the internal resistance developed within the body balances these applied forces. These forces are vectorial in nature and maintain the body in equilibrium under the applied forces. So these are vectorial forces. They have a magnitude and a direction. Now, we know the forces are in different magnitudes and different directions. It is not possible to analyze forces in different directions unless you resolve it into force components along defined axes. So to analyze these forces in different magnitudes and direction, we need to resolve the forces into components through the standard axis system. We discussed the resolution of force components in a video here. If you have any confusion on how to resolve a force into components, please refer to this video here. So for resolving the forces, let's take the body into an XYZ axis system, coordinate system. So you have your X, Y, X axis here, Y and Z. Now the forces, say F1, F2, and let's say this is delta P1, or just delta P because there is only one force shown here. And on the arbitrary cut, there are different areas. You can create as many as areas you want for the analysis of the force. And let's call this area delta A. Now you know this force is standing or is at an angle with each of the axes. So you need to resolve that force into components. Now you have an X component here, which is delta Px, a Y component here, which is delta Py, and an Z component here, which is delta Pz. As you can see, the X component is normal to the area delta A, which is along the x-axis, and that is the normal component of this force. From these force components, we can calculate the intensity of force per unit area, and that term is called stress. So going back to our initial discussion, we have calculated the internal resistance, or we have defined the internal resistance of the generated within the body in here. So this is your component of the internal resistance. This is your internal resistance, say delta P, and you have three components of delta P, delta Px, delta Py, and delta Pz. And the intensity of these forces per unit area is called stress. So you have three stresses here. Usually stress is denoted by tau. So tau xx is delta Px over delta A. The first subscript denote that the arbitrary plane is perpendicular to this axis, and the second subscript denote the direction of the force axis. Plane perpendicular to x-axis, and this is the force axis. So you can see there is two other components as well. So you have two more stresses, that is tau x y, that is the plane is perpendicular to x-axis and the direction of force is y, which is this force here, that is equal to delta Py over delta A. In all the cases, the area considered is the same. And you have one more force corresponding to, one more stress corresponding to this force, that is tau xz equal to delta pz over delta A. So the first subscript denotes that the plane, arbitrary plane, is perpendicular to that axis. Second subscript denote the force axis. Usually the normal force are considered or again classified into two. The normal force is traction forces or compressive forces, traction or tensile. If it's a pulling force, it is a tensile, and if it's a pushing force, that is considered as a compressive. So that is the two variations of normal force. And again, the normal force is usually denoted by a term sigma with a single subscript, which is normal, and the axis of the force is x, is defined by a single subscript. So in this case, tau xx is sigma x, and you have, sometimes you have tau yy, which is sigma y, and tau zz is sigma z. So these are the three normal cases. And the other two forces which are parallel to the arbitrary plane are called shear or shearing stresses. Usually denoted by the term tau, by the notation tau, with the two subscripts, xy or xz or yz, depending on the angle of the plane you consider and the direction or axis of the force. So you have an applied force and an internal reaction. You resolve the reaction into three components, and then you find the stress corresponding to each of the force components. So you will have a normal force and a corresponding normal stress, and two shear forces or parallel forces and corresponding to shear stresses. A normal stress is always denoted by the term sigma, and a shear forces are always denoted by the term tau.